In this video, I will describe everything you need to know to solve calculus optimization problems. First, I will describe what optimization problems actually are. Then, at the 1 minute 10 second mark of this video, I will discuss 5 steps or general guidelines that can be used to solve almost all optimization problems. Then, we will apply those 5 steps to solve an example optimization problem. Let's begin. Optimization problems are one of the most common applications in calculus. Optimization problems are problems that involve the determination of a maximum or minimum value. For example, greatest profit, shortest time are 2 examples of an optimization problem. Other examples include finding the smallest distance or greatest voltage, biggest volume, lowest cost. All of these problems are examples of situations where you're trying to find a maximum or minimum value, which, by definition, is an optimization problem. Although all optimization problems are different, the following 5 steps can be used to solve just about every optimization problem. First, as is the case with many problems in mathematics, the drawing and labeling of a diagram is a good place to start. The second step, and perhaps most important, maybe most difficult step in solving an optimization problem, is to write an equation for the quantity to be optimized, and this equation has to be in terms of a single variable. Sometimes this requires you to think about the problem in a new way or to do a little bit of mathematics, but the equation that you write must be in terms of a single variable. The third step is where the calculus comes in. You will take this equation and you will differentiate it. You will differentiate it with respect to the single variable in which you've written the equation in terms of, before getting to step 4, which is to take that derivative and set it equal to 0. You might be familiar with the process of graphing a function, and when you graph a function, you will take a derivative and set it equal to 0 to find critical numbers, which are places, x values, where the graph might have a high or a low point, or, in the context of an optimization problem, a maximum or minimum. This result will then be used to answer the question posed in the problem. Again, all optimization problems are different, but these 5 steps, or you can think of them as 5 general guidelines, can be used to guide your way through the problem. The next thing that we will do is take a look at an example problem and work our way through these 5 steps to answer the question posed in the problem. The problem is as follows. You are on a beach and want to travel to an island which is 3 kilometers from the shore. You plan to make the journey with a combination of walking and swimming. You are standing 6 kilometers away from the point on the shore closest to the island, and if you walk at a rate of 5 kilometers per hour and swim at a rate of 2 kilometers per hour, a little slower, how far down the shore should you walk before entering the ocean and swimming directly to the island to minimize the total travel time? We will now work through the 5 steps described earlier to solve this problem. Some optimization problems provide a diagram. This one does not. When doing problems like this, I like to begin by reading the entire problem through from start to finish to get a general idea about what is being asked and the situation being described. Then, I read the problem a second time, line by line, drawing a diagram as I do. This problem describes a person standing on a beach. The person's intention is to travel to an island that is located 3 kilometers from the shore. The person is standing 6 kilometers away from the point on the shore that is closest to the island. That 6 kilometers I've now labeled on the screen. The person will be making the journey with a combination of walking and swimming. The person walks faster than they swim. The person will walk part of the journey, and that amount is unknown. We'll find that when we solve the problem. But part of the journey will be done walking, and the rest of the journey will be done swimming. And when the person swims, they will be swimming directly to the island. The person will swim directly to the island. On the screen is the diagram that we can use to help us solve this problem. On to step 2. Earlier, I described step 2 as perhaps the most important, sometimes most difficult, step in solving an optimization problem. Step 2 is to write an equation for the quantity to be optimized in terms of a single variable. It has to be in terms of a single variable. This step will be different every time you do an optimization problem, but in general, what you'll start looking for is the statement where you're asked to minimize or maximize something, and in this problem, we're being asked to minimize the total travel time. So our equation will be an equation for total travel time. Total travel time equals what? Well, if you recall, based on our diagram and what the problem had stated, we are going to be traveling, the person is going to be traveling through a combination of walking at 5 kilometers per hour and swimming at a rate of 2 kilometers per hour. Therefore, at its base, the total travel time will be time spent walking plus time spent swimming. Remember, the time spent walking is at 5 kilometers per hour, and the time spent swimming is at 2 kilometers per hour. So the total travel time will be the distance walking divided by 5 plus the distance swimming divided by 2. If I choose to describe the distance walked with x and describe, so the distance walked with x, that means the total travel time would be x over 5, where x again is distance walking. If I describe the distance spent swimming as y, distance swimming divided by 2 could be expressed as y over 2. So this is an equation that describes the quantity to be optimized. This is an equation that describes total travel time. However, it's not yet in terms of a single variable. We'll have to do a little bit more work to accomplish that. Again, an equation representing total travel time is x over 5 plus y over 2, where x is the distance walked, and that is at 5 kilometers per hour. That's where the divided by 5 comes from. And y is the distance swimming, where the speed swimming is 2 kilometers per hour. That's where the 2 comes in. This is not yet in terms of a single variable. We're going to have to do some math to rewrite this equation in terms of a single variable. We could write this equation in terms of x or in terms of y, but it has to be one or the other. It has to be a single variable. If you look back at the original diagram that we drew in step 1, there is a distance of 6 kilometers along the beach. Distance of 6 kilometers along the beach. Part of that distance will be spent walking. What about the other part? What about the part that I'm highlighting in blue right now? What about this part? In terms of x, what is this distance? If the entire distance is 6 kilometers from the person to the point on the beach across from the island, and they are walking x of those kilometers, the distance outlined in blue would have to be 6 minus x. What I have on the right side of this diagram is a right triangle, where one leg is 3 kilometers and the other leg is 6 minus x kilometers. Again, x represents the distance that the person walked. In this right triangle, you can use the Pythagorean theorem to describe the hypotenuse in terms of x. One leg is 3, one leg is 6 minus x. That means that the hypotenuse would be 3 squared plus 6 minus x squared equals y squared. What is y? We can describe y in terms of x. We'll do 3 squared plus 6 minus x squared. 3 squared is 9. 6 minus x squared is 6 minus x times 6 minus x, or 36 minus 6x minus 6x minus or plus x squared. Combine the like terms to get 12x. 9 plus 36 is 45. I've rearranged the terms a little bit. I've written the x squared first. I've written 9 plus 36, 45 last. And negative 6 minus 6 is negative 12x. That's equal to y squared. If this polynomial, if this quadratic is equal to y squared, what is y? Well, the square root of x squared minus 12x plus 45. This is important to find. We found that y is equal to this quantity. If I replace at this point this quantity with y, I would have the equation for total travel time written in terms of a single variable. Travel time is equal to x over 5, we already had that, plus not y over 2, but instead x squared minus 12x plus 45 over 2. Now we have an equation for total travel time expressed in terms of a single variable. Because we have accomplished this, we can now move to step 3. With the equation written, we move to step 3, which is really the only step requiring calculus. In step 3, we will differentiate the equation. I have the equation on the screen in the form t equals, t standing for total travel time, and I'm going to differentiate this equation with respect to x. Before doing so, it would be, I find it useful to rewrite the equation in the equivalent form. Instead of x over 5, 1/5 x, and instead of this radical over 2, I'll write this as 1/2 times the quantity to the 1/2 power. When differentiating, again, I'm going to be taking the derivative of this total time with respect to x, and the derivative of the first term, 1/5 x, is considerably easier than the derivative of the second term. The derivative of 1/5 x is, of course, 1/5. And to find the derivative of the second term, we will use the chain rule. We'll take the power on the quantity, multiply it by the quantity's coefficient, decrease the power by 1, and multiply then by the derivative of the inside of the quantity. The derivative of x squared minus 12x plus 45 is 2x minus 12. That is chained along as an additional factor. We'll take a step and simplify this second term. There's a few things that we can do to write this in a better form, including multiplying 1/2 times 1/2, rewriting a quantity to a negative exponent in the denominator. 1/2 times 1/2 is 1/4. I have that 1/4. I have the 4 in the denominator. 2x minus 12 I've written in the numerator, factored a 2 out to the front. And the quantity to the negative 1/2 I've rewritten as a quantity to the 1/2 in the denominator. One last thing to simplify this. 2 over 4 in lowest terms is 1/2. So the simplified version of this derivative is 1/2 plus x minus 6 over 2 times the square root of x squared minus 12x plus 5. This is the result of differentiating the total time equation with respect to x. I described step 3 as the calculus step. Step 4 is the algebra step. We are going to be doing a lot of algebra in step 4 when we set the derivative from step 3 equal to 0. In this problem, and is often the case in optimization problems, the majority of the work, the most work that is required for the problem will happen in this step. Again, step 4 is to set the derivative equal to 0. And like many mathematics problems, there's more than one way to approach this problem, more than one way to do it. I'm going to present what I think is the most efficient way to solve for x. The first thing that I'm going to do is rewrite this equation by subtracting 1/5 from both sides. This is somewhat of a complicated equation still to solve. One of the things that makes it complicated is that there is a square root involved. There's a radical in the denominator of the fraction that's on the left side of the equation. First thing I'm going to do is eliminate that radical by squaring both sides of the equation. I'll square both sides. When I square the left side, this radical will be eliminated. When I square the left side, this radical will be eliminated. I'll also have to deal with squaring the numerator x minus 6 to the second power. Remember, x minus 6 to the second power is certainly not x squared minus 6 squared. It's x minus 6 times x minus 6. And you'll go ahead and multiply that out. X squared minus 6x minus 36 is x squared minus 12x plus 36 when you combine the like terms. We'll square the 2 to get 4. We'll square the square root of x squared minus 12x plus 45. Squaring a square root are inverse operations. That will cancel each other out. And on the right side of the equation, negative 1/5 squared is 1 over 25. I'll rewrite this in a quick step of distributing the 4. All that has been done from the left to the right side of the bottom of the screen is I distributed the 4. We're well on our way to solving this equation and finding the value of x. When you have two fractions equal to each other, you can think of that as a proportion. And if this were a proportion, the way that I would probably solve it is by cross multiplication. And that's what I'll do here. I'll go ahead and take x squared minus 12x plus 36 times 25, and then 4x squared minus 48x plus 180 times just the 1. I'll distribute on the left side of the equation, I'll distribute the 25. No need to distribute the 1 on the right side. The numbers will get pretty large in this problem and often do in optimization problems. 25 times the quantity of x squared minus 12x plus 36 is 25x squared minus 300x plus 900. I'll drop the parentheses and the factor of 1 on the right side of the equation. And it may become apparent here that we're dealing with a quadratic. This will actually have two solutions, like all x squared quadratic equations do. I'll go ahead and move the terms on the left side or the right side of the equation over to the left, subtract 4x squared from both sides to get 21x squared on the left, add 48x squared or 48x to both sides to get negative 252x, and subtract 180 from both sides. 900 goes down to 720. At this point, we have a quadratic equation. We can use the quadratic formula to solve it. To solve 21x squared minus 252x plus 720 equals 0 using the quadratic formula, we'll first recall the quadratic formula. I think that if you are doing an optimization problem in calculus, you're very familiar with the quadratic formula and have used it many times in the past. It is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, where the coefficient on the quadratic term is a, the coefficient of the linear term is b, and the constant is c. So we'll simply substitute the values of 21, negative 252, and 720 for a, b, and c respectively into the quadratic formula, and we'll be done with step 4. We'll have set the derivative equal to 0. So negative b in this case will be the opposite of negative 252, plus or minus. This is where the two answers come in. The square root of b squared minus 4 times a, 21, times c, 720, all over 2a, all over 2 times 21. Can do some simplification here, including realizing that the two negatives in front of 252 will cancel out. The first term in the numerator is positive 252. Negative 252 squared is positive 63,504. Again, numbers in optimization problems often get large, even if they are not in the original problem, and the final answers are often not very large. While doing the work, you may run into some large values. And speaking of large values, the product of 4, 21, and 720 is 60,480. Under the radical sign, the subtraction results in 3,024. So we have 252 plus or minus the square root of 3,024 all over 42. Our two solutions will be, after adding 252 plus 3,024 over 42, we'll get 3,024 is not a perfect square. Both of our answers here will be irrational. Adding those terms in the numerator yields 7.3093. And when you subtract the terms in the numerator divided by 42, we'll get 4.6907. Those are the two values that we get when we set the derivative equal to 0. We'll answer the question in step 5 now. I described step 5 as interpret the result to answer the question. So remember that the question here was if we walked at a faster rate, 5 kilometers per hour, and swam at a slower rate, 2 kilometers per hour, how far should you walk down the shore before entering the ocean and swimming directly to the island to minimize the total travel time? Minimize the total travel time. We drew a diagram. Realize in this diagram we just found a value of x that optimizes the situation. X represents the distance walked. X represents the distance that the person would walk in this situation when we are optimizing total travel time. Let's take a look at the values we found for x. We found that x could be 7.3093 or 4.6907 when we set the derivative equal to 0. There is only one optimal value. Let's think about the first number, 7.3093, and look at the value of x. The person in this situation was standing 6 kilometers down the shore from the point where the island was at the closest point the island was to the shore. So an answer of 7 does not make sense here. We're certainly not going to walk down the shore 6 kilometers and then 1.3 kilometers more and swim back towards the island. That would certainly not minimize total travel time. On the other hand, the value, which is approximately 4.6907, this is the optimal value. In this problem, the domain, the possible values for x, are between 0 and 6. The optimal values are between 0 and 6. 7.3 is not in the domain. 4.6907 is, and it is the optimal value in this situation. That's the value that will minimize total travel time. I'm going to round this answer off to the nearest hundredth and state a solution of you should walk about 4.69 kilometers along the shore before swimming to the island to minimize total travel time. Thanks for watching. I hope you learned something.